There were two parts of this lab. In the first part of the lab, computer simulation of a planet in orbit around a black hole was used to approximate the mass of the black hole. This was done by using the perpendicular and parallel components of the net force and using that compared with the gravitational force to approximate the mass. And in the second part, now we have all the information of the black hole, including its mass. We were able to calculate the distance, the speed required for a rocket ship traveling near the black hole to continue its path harmlessly and not be sucked into the black hole. Here you can see some of the results. I won't get into it too much for time constraints, but they're there to see. Some relevant formulas here are Newton's second law, which states that the change in momentum is equal to the net force times the change in time. And we can understand this change in momentum in two different ways. Typically, when in non-circular motion, the change in momentum is really just the acceleration, the change in speed. But here you can understand it as the change in speed, but also the change in the direction of motion. And that's what the parallel and perpendicular components are. The parallel component is the change in speed, which you can see by this tangent vector here, which looks like a typical tangent in a two-dimensional calculus would look like. And the perpendicular component, which points towards the center of the oscillating circle and is perpendicular to the path of motion. The perpendicular component is responsible for the change in direction. Some other formula used were the formula for gravitational force, which states that the gravitational force is equal to the gravitational constant times the masses of each planet divided by the distance between the planets squared, pointing towards the planet, or in this case, the black hole. And the position and velocity update formulas, which have been used multiple times just to update the position and velocity, and are very intuitive formulas. The first computational model for part 1 is responsible for calculating the mass of the black hole, or approximating it by using the parallel and perpendicular components of the net force. Using a timestamp of 1 day, which is equal to 164,000 seconds, the net force acting on the planet from the black hole was calculated from the randomized velocity in the model, and then used to approximate the mass of the black hole. And as showed earlier, that average mass of the black hole in all 506 timestamps was about 8.19 times 10 to the 33rd kilograms. So here you can see the code. This part's not as important, setting the mass of the star equal to 2 times 10 to the 30th and setting the time stamp for delta t. Now, the chunky part of the model, you can see how the momentum is calculated, and then that momentum is broken down into the parallel and perpendicular components of the net force, and then how that force is used to approximate the mass of the black hole by manipulating the gravitational force and isolating it for the mass, because we have the net force in the perpendicular and parallel components. The second part of the model is going to calculate what speed a rocket ship starting near the black hole would need to escape, being sucked into the black hole. Because now that we have the mass of the black hole, we can use the gravitational force formula to see what the magnitude of the force acting on an object, or we don't have to do any algebraic manipulations this time. Because the planet is still there, there are two gravitational forces going on the ship, one from the planet and one from the black hole. And we use this net force to update the position and velocity of the ship in order to see if it can make its escape. So looking into the code, we see how we plugged in the number for the mass of the black hole at the very top, 8.19 times 10 to the 33, and everything else stays the same. Ship of 7 times 10 to the 10th, sorry. And here we can see calculating the planet of the speed and velocity, and the next part, calculating the position vector on the planet and the ship, using that position vector to calculate the gravitational force on the planet, and then on the ship. It repeats a handful of times in calculations like that, and then the velocity of the planet and the ship are updated, and you can see that the ship makes its escape with the velocity that we input if you run the model. So using the parallel and perpendicular components of net force, here are the results. Touched on that a little earlier. And discussion, well, what does it mean? Because the net force is proportional to acceleration, the net force in its perpendicular and parallel components are responsible for dictating the acceleration or rate of change in its direction and change of velocity. And once again, we typically think of acceleration as change in velocity, but in this case, it can be broken down into components, and that acceleration means a change in the direction. If it was 0, it would just travel in a straight path. And what if we wanted the black hole to escape? or to orbit around instead of escape. Well, those calculations are complicated, but the general idea would be it would need to have a higher velocity because then have higher velocity because using the formula for a perpendicular component, which is mv squared over the radius, the change in the perpendicular component would be higher with a higher velocity, so it would be orbiting more. So it would be able to orbit the black hole without